Okay, now let's go on, and now let's look at the left-hand side of the equation. So let's look at the left-hand side. Okay, if we integrate this from S1 to S2 of Fs ds, what we're going to do here is we're going to say, well, you know what? This can be also written as, if we look back in the vector method, this is going to be force times the ds. We're looking at the force and we're dotting it with the ds direction. And if you remember, the dot product between two vectors is a scalar. So just kind of, I'm showing it in different forms. So maybe something, one of these two ways might be the preferred way for you to look at it. And we know that force times distance is equal to something called work. We looked at that in dynamics. And what we're doing is we're transferring work to that body. We're taking we're taking something and we're applying a force to that, causing it to work. Force is applied to that body, transferring energy from that force to the body. That's what we're doing. Okay? So work is going to be in units of newtons times meters in SI, which is going to be equal to a joule, which we're going to say is capital J. This is our SI units. And in English units, our force is going to be a pound force, and our distance is going to be a foot. And so we're going to get pounds force feet. But that's not what we use in English units. We're going to have to convert here. And we're going to say that 778 pounds force feet is 1 BTU. And this is what we're going to do in English engineering units. Okay, so we're going to convert to BTUs. And so there's going to be this conversion here that we have to think about. Okay, again, SI is nice and kind of compact, but English engineering units, not that easy. We're going to have to always convert because the units of energy in English engineering units are BTUs, not pounds force feet. Okay, so let's go and do that conversion, divided by 778. Okay, now, let's look at the units. That's the units of work. If we're looking at our equation, we have to have the same units on the right-hand side and the left-hand side of the equation. So we have joules. We must have joules on the right-hand side and left-hand side of the equation. So let's look and see the units of kinetic energy. Okay, what do we say? Kinetic energy was 1/2 mv squared, right? Well, 1/2 has no units. We don't have to really worry about that. That's a constant. But in SI, our mass is going to be in kilograms. Our velocity is going to be in meters per second, and we're going to have to square that. So we're going to end up here with kilograms meters squared per second squared. Okay, so the conversion that we're going to have here is we're going to say that in 1 Newton is 1 kilogram meter per second squared. That's a fact. That's multiplying it by 1 in a very kind of tricky way, I guess. We're looking here at F equals ma. We said 1 Newton is equal to 1 kilogram times 1 meter per second squared. Multiplying it by 1. No big deal there. 1 meter goes away, seconds go away, kilograms go away, and what do we end up here with? Newton meters, which is equal to a joule. So directly, right away there, SI, when we multiply, we do kinetic energy, we have units of joules. No big deal. No big deal. Okay, let's look at English engineering units. Here's where that pound force thing comes back in. 1/2, no units. Pound mass is going to be a pound mass. Velocity is going to be in feet per second squared. Feet per second, squared. So this is going to be pound mass, feet squared per second squared. Okay, now, no, I have to get units of energy. And so I'm going to have to come do something here to get a pound force. So I just can't say this pound mass is equal to a pound force. I can't do it. I'm going to have to go through the first conversion and say that 32.2 pound mass feet per second squared is 1 pound force. Okay? And so, here we go. Get rid of pound mass. Let me use my orange here. We get rid of pound mass. We get rid of one of our feet. We get rid of our second squared. Now we have foot pounds. And now we do another conversion to say that we're going to say 778 foot pounds is 1 BTU. So this is probably a better example than what I had earlier in that first video. Why we need to convert pounds mass to pounds force. Here's a very good example. We just can't say this pound mass is equal to a pound force. We just can't do it. Even though this kinetic energy is found on Earth, we can't say that a pound mass is equal to a pound force in here. We have to convert our units and make sure our units all work out. Okay, once we have our units all work out here, now we say we have BTUs. Okay, so it's even more illustrative of a fact when we get down to there. Okay, now one thing you can be for sure is that, again, SI is very easy. You just multiply it through. In fact, you could forget to convert your units and you're going to luck yourself out. But English engineering units, it's not the case because you're going to have to go through these two conversions, divided by 32.2 and divided by 778. And you'll see in my old exams, I like to ask you these questions. I like to make sure that you understand things in this way. Okay? So, what I want to say here before we move on to potential energy is we are taking a object, we are applying a force to that object, transferring energy to that object where it is stored as kinetic energy. That's what's happening there. That's what's happening in this situation. Now let's go on and move on and talk about potential energy. Okay, now I'm going to take that same ball or whatever particle, and now I'm only going to look in that z-plane. Okay, now that ball, what color was that ball? Green. And we'll look at this. This is our system. Now what I want to do is understand that there's a force acting on this that's trying to pull it up. Here's my force R. And you're pulling down is gravity, mg, pulling down. These are these two forces acting on it. I'm trying to pull that particle up. Gravity is trying to pull it down. And as we're doing that, we're going to go from a position Z1 to a position Z2. Okay? Now, we're not concerning, it could also be moving in the XY plane, but we're not worrying about that right now. I'm only worried about that Z component of it. I've broken up that Z component of it. And remember this point right here, this is our datum. This is our datum. We need to have a datum someplace. It's going to cancel off eventually, but we just need to know that it's there. Okay, so here's what we had from previously. We had the integral of f ds is equal to 1/2 m v2 squared minus v1 squared. That's what we had from our previous analysis. Okay, this here, this force has external forces and gravity forces are included in this analysis. Okay, I did not determine which forces I was talking about. Any force acting on this particle is going to be included here. Okay, so I'm going to break it into two. I'm going to say, well, I'm going to have from Z1 to Z2 of my force R times dz, and then I'm going to have minus a Z1 times Z2 of mg dz. Okay, so this here is going to be the work done by R, and this is here is going to be the work done by gravity. Okay, there's two places, two things we're going to work with there. Now notice I have a negative sign. Why do I have the negative sign? Well, because that R force is acting positively up in my positive direction, and the gravity is acting negative in my opposite of where I'm trying to go. Okay? So I only now want to work on this work done to gravity. That's due to gravity. That's what I want to analyze first. So let's look at work due to gravity. Okay. Integral from z1 to z2 of mg dz. That's what I want to analyze. Well, we know this is very easy. Mass is constant, comes out of the integral. Gravity, we're assuming, is constant, comes out of the integral. Now we have the integral of dz, which is just z. Okay, so this is going to be mgz times z1 to z2. Or it can give me mg z2 minus z1. Okay, that's what we have here, which we know this is our gravitational potential energy. Gravitational potential energy. So that is breaking up that one piece of that one special type of work that's happening there, that force and that gravitational work. And so we can say here that we can write this as mgz2 minus mg z1. We can write it as mg times z2 minus z1. I can write this as the change in potential energy, or I can write this as potential energy at state 2 minus the potential energy at state 1. A little delay there on my transferring of notes to the video. So I'm going to ask you again. I'm going to pause the video here again and ask you the question: is potential energy a property? Again, remember what you learned about properties. Is potential energy a property?